Okay, hi everybody. I'm Malcolm Sparks, and I'm going to be talking of reflections on a real-world Clojure application. A little bit about me first. My Java history, I started with Java in about 1995, but only really started using it when you could start doing server-side Java in 97. I started a company called EJB Home, which was a forerunner of application servers at the time, and that became a full-blown J2E application server in about year 2000. So I was involved in the J2E specification committees. 2003, I left the company I was with, Iona, to start a company called J-Coverage. I found a way of doing code coverage in bytecode, and with Peter Morgan, we built a code coverage tool, which became clj-logging-config, by the way. Then after 2004, I was an agile consultant and did a number of TDD training courses and joined an investment bank, Deutsche Bank, which really coincided with my discovery of Clojure. My Clojure history kind of began in 2008 when I was looking for something a bit more dynamic than Java as I was writing a build system. And I came across Clojure and kind of discounted it because I think I didn't like the source code or something. But in 2009, I discovered it again when I was trying to write a web service for the bank, some HTML, and I found it very, very quick to use. I led the functional programming special interest group at Deutsche Bank, and in 2011, I had an opportunity to create a very large, or start of a large Clojure system, where I got kind of honed my real Clojure skills. Last year, I gave a talk similar to this called Reflections on a real-world Java Clojure project, which you can get online. I'm not going to give that talk again. I'm going to give parts of that talk, but this is a new talk. Right now, I'm working with Clojure full-time in Tech City with Likely, and I've just founded a Clojure training and services company called Juxt. So I mentioned I gave a presentation like this last year. I don't know if you've ever bought a book of essays where the book is named after one of the essays. Well, this is like that. I've got a few different things to say, and in my last talk, I did make a throwaway statement about mutable state. And I want to spend a bit more time going over why mutable state is an important concern. Then I'm going to try, because this talk is about Clojure, I don't know how many of you know Clojure. I'm going to try an experiment of trying to just give you an overview of the syntax of Clojure in 8 slides. I'll try and do it very quickly, and you can let me know afterwards how I did. And then I'll move to the main body of the talk, the reflections on a real-world application. Then I have a mystery section, and then we can do some Q&A. Okay? So, mutable state. We talk about mutable state and immutability all the time, but it's quite a recent word. It's only recently it's become part of our programming lexicon. And I want to tell the story of mutable state, or particularly in Java. And for me, mutable state really begins back in the year. Does anyone want to guess what year this was? 90, who said 97? Well done. Yes, it's 1997. That was you can tell by the phone that was actually a very, very long time ago. In those days, phones, as you might remember, had these protruding aerials that came out, and if you dropped your phone on the street, you could pick it up, and there was no danger of your glass breaking. You'd have to drop it pretty hard to break one of those things. Like prime ministers and footballers, apart from David Beckham, of course, technology didn't have to be good-looking to succeed in the market. And Java was released in 1997, or at least Java 1.1, and this is what it looked like. This was the Java beanbox, and what you could do is create Java objects, and if you were to give them what are called setter methods and getter methods, they would act as properties, and then you could visually inspect these properties and change them. Now, why on earth did Java do this? Why did this happen to an OO language? Surely this is just awful. What they did is make it an idiom for Java objects to have getters and setters. Prior to this, some objects did and some didn't, but it wasn't encouraged. After this, if you didn't write a getter and a setter method in your object, then your object couldn't play in the Java beanbox. So everybody wrote getter and setter methods for all of their code. Why did Java do this? Because the dominant programming paradigm of the time was this. Does anyone know what this is called? Yes, Visual Basic. This was the most successful dominant programming paradigm, and Visual Basic had these controls called VBX, which you could drag and drop, and people were very successful at creating quick applications, reliable applications in Visual Basic. And the property sheets on the right-hand side, because of the visual nature of Visual Basic, you could expect visually a programmer to kind of contain all that state in their memory and to be able to manage it. But the problem was that Java's mutable state encouraged a lot of bad behaviors in Java. And I would like to say that mutable state and getter and setter methods broke encapsulation in Java. And we've been struggling to unbreak Java ever since. And it's quite a statement, so I want to assert a few problems with setter methods. The main problem is that setter methods cause side effects in your code. I contend that programming with mutable objects makes things more complex because there's more state changes and more states to code around. That makes programming harder. It certainly makes debugging harder when you can't be sure when a particular variable has got a certain value. You can't say that that's fixed. You don't know when it might change. It certainly makes concurrency harder because every time you have something that's mutable, if you want to change it, you have to lock it in case there's other threads. Not so much of an issue in '97, certainly an issue today. And the culmination of these effects have made Java less stable and slower. Here's a birthday class. This is an idea I stole from Eric Normand, and he talks about your birthdays being something that's kind of unchangeable. Everybody has a birthday, and nobody's birthday changes. So let's model that. We've got a getter and a setter. Great, we can play in we can be loaded into the Java beanbox. And if you look down there, I've created a date. 96 to 27. Anyone want to hazard a guess what date that is? It's the 27th of March, 1996, which happens to be my son's birthday. He's actually 17 today, so I'll say happy birthday to Daniel. I love you very much. Yeah. The second thing about the date, on the second date setting, is something quite surprising. We've set Daniel's birthday, but then we've set it again to something else. Surely that should be impossible. So let's get rid of our getter and setter methods and create something more immutable. So we do that. So we create another date, 12/12/12. Anyone want to guess what date that is? I'll explain it. It's the 12th of January, 1913. Okay, we love Java, but here we've created a date, we've created a birthday with that date, and we've got no setter methods. But then lower down, I can set the month on that date and suddenly make it July. So we've been able to change somebody's birthday again, even though there wasn't a setter method. And that's because date has setter methods. What if we do this with, what's the problem of side effects? Not so bad with birthdays, but just imagine you create a person class, and on the left-hand side, if you look at that code, the person is modeled with a list of payments, and the person gets given an envelope with some money in it. Great, got some money. And then the definition of the envelope was that it had setter and getter methods. So you could pay the person the envelope, sealed envelope, give it to the person, and then later on, you could decide to change the money in that envelope that you'd given to that person. You can't possibly write systems like this, can you? We do it all the time. And this is what brings the complexity of mutable state. Let's alter it a bit. Let's try and create a birthday with a string. So we create a string, 4th of December 2012. Now let's set a birthday. And now let's change our string. We did date to substring. What's happened to the original date? The answer is nothing. It's remained as it was. The reason for that is that strings have a property called, they're immutable in Java. And this is a fantastic property, and it would be great if all of the objects in Java were immutable. Because once they are, you have this safety. Once I give somebody a birthday, I can guarantee that that birthday can never change. And I can then, because I've got that guarantees, I can copy that birthday wherever I like, and I don't have to lock it, because I'm never going to have to change it. So it's safe for concurrency. So you might think that, well, as long as we just program without setter and getter methods, everything's going to be fine. But the trouble is that mutable state is everywhere in Java. Take the new collections classes. Here I've made the collections class final, so I'm creating a list of dates. This is for people who have 2 birthdays, like the Queen, or you might have a classroom of children and you want to store their birthdays. But here, I've been able to construct the birthdays class with some dates. And then just as I did before, I've been able to mutate that list by adding something to it. And now, a class that had 1 birthday when it was constructed now has 2. And that's another side effect. So what can we do? And there are some people that suggest that this is what I used to do. I used to use Google collections, or what are called Guava collections. And Guava collections allowed you to build immutable lists so that we can do the same thing, but look at the last line there. If I try to add a new birthday, it's going to throw an exception. The problem with immutable classes is that whenever you do actually want to create a new collection, which is a clone of the old collection, you have to accept the performance trade-off of copying everything in that collection to a new collection. And that performance trade-off isn't something that a lot of people are willing to sacrifice, willing to make. But certainly, this was the way that I was writing Java code prior to 2009. And Guava code also has a lot of functional programming idioms in it. And there's something I ripped out the Guava docs to explain really how I was writing code. The code that I started writing in Guava ended up being very, very verbose and confusing and certainly unreadable. And an example here is on the left, the kind of code I was writing, and it was really horrific. And certainly couldn't convince other Java programmers that functional programming was a good idea. So it was at this point that I discovered Clojure and I started using Clojure. But from a Java point of view, if we go back to the beanbox, the fact that all the objects have setter methods was really a case that the genie is out of the bottle. There is so much mutable state out there that even by writing new Java code, which doesn't have mutable state, there's still a huge amount of libraries that would have to be rewritten, as it were, to benefit from immutable state. So that was why I elected to use Clojure, really because I wanted immutability in Java. Now, rather than rewrite everything in Java, what I really felt that instead of trying to get everybody to agree that mutable state was a bad idea. I discovered that with the closure, it's just a tool. And if you bake good practice and good technique into a tool, then it scales. And if you can get other people to use it, as long as you've got immutability at the heart of the language, then you can all reap the benefits. So I'm going to try explaining closure. Could you just raise your hand if you know the closure syntax? Or so about, okay, not many. So I'm going to try and explain, give you a quick kind of overview of closure in 8 slides, and let me know how you think I did. So we start off with the thing that puts everybody off closure and Lisps in general is the brackets. And I'm just going to explain why the parenthesis in closure makes sense. We can start off with the calculation you learn at school. 2 plus 2 is an infix notation. And everybody's uncomfortable. A lot of people are uncomfortable when you can't write 2 plus 2 in a language. The trouble with infix notation is that it's ambiguous. There's certain cases where we have to have operator precedence rules, and eventually it gets just too much, and we start writing a different notation where we put the name of the function, like, for example, sine of 30 degrees. So we bring in 2 notations because the infix notation doesn't scale, and it doesn't scale beyond 2 operands. It doesn't work very well as a unary operand. What Lisp does is that it says, rather than having different notations, just let's have one, and let's fix these problems and just have one that scales. And we'll write things in prefix notation, and we'll just write everything in the same way. We will put everything in brackets, so there will be no ambiguity as to what gets evaluated first. And then we'll have no semicolons and no white space. And if you can accept this trade-off, then you can write in Lisp. Now, code versus data. In Lisp, everything you can do in code, you can do in data. It's very, very declarative. You don't have to do code in Java and data in XML. It's very powerful. Everything that I've done on the left there, you can do on the right. So in the adding up numbers sense, I've got on the left-hand side an operator plus and 1, 2, and 3 to make 6. But it may be that I want to have just a list of plus 1, 2, 3. When you use a parenthesis in Lisp, it gets very excited and wants to evaluate it straight away. So if you don't want that and you just are talking about a list, then you use square brackets. I think of the square brackets as a kind of box where you can put data in. There's a way of creating maps, which I've done on the left, but if I want a quick way of doing it, I can use curly braces. And then on the left-hand side, there's another notation, a cheat notation for sets with a hash in front of curly braces, but they're not used very much. But the nice thing about the notation for data literals is that I can nest them. So I've been able to create a data structure on the right very, very quickly without a lot of boilerplate. Functions in Clojure. The first 3 functions are all the same. What we can do is we can create a function with an fn operator, which takes a list of arguments, and then you have the implementation. And once I've created that anonymous function, if you like, I can put it into a box called a var. And in this case, I've named my box Pythagoras, and I put the function in the box. In every Lisp, you just get a lot of boxes, and they've all got these names. Because we write that a lot, there is a way of getting rid of boilerplate in Clojure, which I won't talk about, but that's by using macros. And defn is a macro which expands the second line into the first line. And finally, there's a way of creating very quick anonymous functions, because they're created all the time, and that's used with a little hash before the parenthesis, which means I'm making a function. And then I can reference my anonymous arguments with %1 and %2. Now, the fourth example is a closure. And this is where we've created a function, but the function is referencing something that's outside of the function, in this case, x. So I might want to create a Pythagoras function where I actually fix one of the sides. And this is how I would create a closure. So as you can see, it's all very, very simple syntax to create functions, because in Clojure, we create functions all the time. My slide 4 out of 8 is sequences. Sequences are very, very important, and you can use sequences for... We have all sorts of sequences in programming. We have Twitter feeds, we have SQL results, we have HBase tuples. All kinds of things can be thought of as sequences. And this a simple sequence is a range, which just gives you a sequence between 1 and 10. If I can model things as sequences, then I can have a bunch of functions that can do things on the sequences. Number one, I can map an existing function over a sequence. What that means is that I'm going to apply a function, or call a function on every single element of that function, of that sequence. So number one there, I'm taking a range of numbers and I'm decrementing each one. So I'm going to have the same set of numbers, it's just I'm going to take one off each one. That's a mapping function. It takes a sequence and returns a sequence. Second important one is reduce. That takes an operator and applies that operator against everything in that sequence, building up a result. So if I want to add up an infinite number of numbers, I can reduce plus on that range. Of course, that wouldn't work because it would take forever. But the thing about sequences and all of these operators on the right is that they're all what are known as lazy functions. So they don't get applied yet. They only get applied when something that's non-lazy calls them. And this allows you to create a computation that's going to be build-up computation that is lazy. So you can build up quite big computations without running out of memory. And I'll talk about that a bit later. So slide 5, we talked about collections and the Guava collections before. What do collections look like in Clojure? So on the left, I'm dealing with lists. On the right, I'm dealing with maps, which are the two most common collections in Clojure. On line 1, I'm taking a list of letters. So let's make letters B, C, and D, 3 letters in a list. Conj takes that list and returns a new list with E added onto the end of it. Cons is really a kind of throwback to LISP because that's when the argument does the same thing, but it puts something at the front of the list. I can count the letters, and I can 4, 5, and 6. I've actually taking the first character of each letter, because I can treat strings as lists. On the fifth one is an example of composing a function quickly. What happens if I wanted to take the first letter of each list and take it and convert it to its ASCII equivalent? That's doing 2 things at once. Well, I can compose those 2 things at once into a third function with comp. And in line 6, I can map a function, in this case, a function vector, and I can map it over a list of letters, but also I can include a second set of parameters or a third set of parameters. And in this case, I'm wanting to give return some pairs where B is set to 0, C 1, and D 2. Now, the neat thing about all of these things on the left is that instead of changing the original letters, they've created copies and then changed the copy. But they don't actually, underneath in Clojure, there is no copying. It's known as structural sharing, and so you don't get the performance hit. But everything right down at the very bottom of every single data structure in Clojure has this property, and it's called being a persistent data structure. It has the property of not changing the original, which means that if somebody's got a reference to the original, then you're not affecting them. You're not creating a side effect. Exactly the same. That's quite easy to think about. How would you do that in lists? Because you could do that with links and pointers and so on. One of the neat tricks that is done in Clojure is that they achieve the same property with maps, which is a lot harder. So these are all of the, not all of them, but a selection of things that you could do to a map. So let's take a map where we've got the conference DevOps in the year 2013, and we want to create a new map, but one that has the location of London. We don't want to change the original map, but we want to create a new one. That's what assoc does. Dissoc does the opposite and takes something away. Merge takes a new map, merges it with the old map, and creates a new one. Seek takes the map and turns it into a sequence, because we have so many operators in Clojure that deal on sequences, so it's quite handy being able to turn a map into a sequence of pairs, and so on. Just 3 more slides to go now. Special forms. If the if operator, who's used if in a programming language? We all have. The if operator was invented by John McCarthy, the founder of LISP. Actually, he contributed it to Fortran. So if you've ever used if, you've got John McCarthy to thank. But very, very simple. If you want to do an if in Lisp, you take you create a list. You've got if. The next thing is an expression, and then there's two more expressions. The first one is evaluated if true. The last one if false. Pretty easy. When is like if, but doesn't have an else. So when you can do all sorts of things in the body, and it will only happen on the true clause. And then for and a bunch of other ones. So these are the things that we would expect. The last one there, taking all of the lines out of a text file, and I think for each line, count how many characters in the line. So we're almost there. One of the wonderful things about Lisp is that if you find yourself writing a lot of boilerplate, chances are there's a macro that can collapse it again. And this feature has allowed new ideas and new language techniques to be added to Lisp without actually anybody, they can be added after the Lisp language has finished. So you can add it as a library. So for example, taking the, there's a feature that C# has that Java hasn't ever had, which was this using idea, which you can say, using this open stream, I want to do something with this open stream, and then I want to make sure that you close it afterwards. I don't want to have to call close on it. So in Java, we always have to remember to close, we create finally blocks or whatever to close our streams. In Clojure, this can be done with a macro, where in this case, the code that gets generated by this with open macro is one that remembers to close or call .close on R when it's done. So you don't have to remember to do it. You can just wrap it in another list. The one on the right-hand side is another macro which is very often used, which is called a threading macro. And if you remember the previous slide where we took an existing map and then we created a new map from it, what happens if we wanted to create, we wanted to keep modifying the map in all sorts of different ways, taking the previous result and putting it into the next function and create a pipeline. And this is how we do it. It's very, very quickly to make all sorts of transformations on a data structure. Each one of them yielding something that acts like a copy of the previous one. And when you have all of this immutability in a language, it actually makes concurrency far better, far safer, because you don't have to lock so much. But sometimes you do need to have mutable state. And Clojure offers, instead of setter methods, Clojure offers 3 ways of creating things that are mutable. But you can't set them. In order to change them, you have to send a function into them. In the case of if I have a account, which perhaps is a count of the number of users logged into a system or something, and I want it to be immutable, a single value that I want to be mutable, then I call it an atom. In order to change an atom, I can't just set it. I have to send. I can set it, but I can also send functions into it. But the thing is, anybody who's at the same time trying to read the value of the atom won't have to lock. They will just get the previous copy of the atom. If they're in a different transaction, they'll get exactly, it will work just like a transaction does in a database. They will see that atom is 3, even though it might have been incremented to 4, 5, and 6. In my second example, 2 accounts, I might want to, if I want to take £50 out of one account and put it into another, I can do that atomically using a dosync function. In the case of, that's a classic example of a deadlock in Java. If I was to do that in Java, and I was actually going to put synchronized on the Java method for incrementing and decrementing accounts, I could very easily hit a situation where the first account gets incremented and the second account gets decremented, and somebody's trying to move money the other way, and then there's a deadlock. With Clojure, that can't happen because all of the changes to these refs are done through the software transactional memory. On the right-hand side, there's some other useful concurrency primitives. Future, which allows me to take a function but defer it and to actually run it in another thread. And then when I ask for the value of it, potentially the thread will block until there's a value available. So the support for concurrency is very explicit in Clojure. There's no kind of just setting of state. When you do want to have a state, you have to go through the very strict software transactional memory that it provides. And this is what gives Clojure its safety. So now we come to my reflections on building a Clojure application in a bank. And some of the things that I remember really stuck out as being kind of surprising sometimes in what made it different from my previous experience building Java applications. And I have to say that I found that once I'd discovered writing Java using what they call constructor-based dependency injection, i.e. avoiding all setters and trying to make everything final. If I had the opportunity to write code exclusively in that way, I did find that overall systems written to that technique were more reliable, and they didn't have so many state issues. So if we combine that with, I think, the fact that there's so much laziness in Clojure means that in our application we were able to create most of the processing actually ran as a stream that just took from data from disk, did stuff with it, and sent it out to a browser or sent it out to a spreadsheet or something. And there wasn't any state being held in memory. It was all a stream of computation. And that really helped to keep memory down. In fact, when we hooked up Visual VM to it at one stage, it was just bumping along at the bottom because there wasn't any memory being used. So I think if you can exploit laziness, you can avoid actually using memory. I certainly think that wasn't the only reason for the stability. That certainly using other things like Git and giving quite a deal, some care and thought and diligence to the programming process with these ingredients in place does actually yield reliable and solid systems. So I think this is for me, this is a reliability trick. If you can get the safety in Java without the using good technique, then that can work too. But Clojure is just a tool that has these good practices built into it. I was very against using null in all of my Java code, and a lot of people share that idea. And I was very struck by how Clojure doesn't really have any problem with nulls because it treats them as values. But what do I mean by that? We don't see many null pointer exceptions because all of the functions are quite happy dealing with nil as the value, and will more often than not return something sensible. So if you have a nil map and you try to get a key out of it, then it will just say nil. If you've got a nil list and you ask what's the first element of this list, it will say nil. And it's only when you start hitting a Java library that you start getting null pointer exceptions. So if you can have nil without null pointer exceptions, it's useful. Certainly think that a laziness was something that was quite a difficult thing to learn in Clojure. So it's quite a surprise when you build up a big computation and you think, well, why hasn't that run yet? And that's something to watch for if you're dealing with Clojure from a beginner's point of view. Whenever you're using sequences and they're not working as you think they might, you always think, well, have I actually executed that sequence yet? I did find that after we'd written about, 10,000 lines of Clojure, we did start finding some of the functions got really, really big. And I think that can be true for a lot of functional programming languages applied to real-world problems where you have all sorts of other things to deal with, like the configuration of the system and database resources and lots of moving parts. It can be quite hard to reduce your functions down to this kind of really, really small pure functions again. And certainly this was a problem for us. But towards the end, we discovered that actually rather than functions actually knowing about the next stage in the processing pipeline, it was better to break functions out and just have functions that take stuff off a queue, do something with it, and put it on another queue. Because the great thing about queues is that the thing in queuing the data on the queue doesn't have to know or care what the subscriber of the queue is going to do with that piece of data. So, yes, it's hard with testing a large Java application. You often find that the best applications, the ones that have got the most tests around them, are the ones that are easiest to refactor, and they're the applications that need less refactoring. The problem systems are the ones that are huge Java systems, lots and lots of spaghetti. You can't refactor it without running the tests, but then there aren't any tests. And you're in this catch-22 situation. And I think the main difficulty with complex Java systems is the number of side effects that actually go on. And when you create a big test suite in Java, a lot of what you're doing is trying to ensure that the same side effects are happening, and that you're not going to be caught out. And really what a mock object does is collect all the side effects that are happening as you inject a mock object into a piece of code. It might be what you're sort of measuring is making sure that all the side effects are happening to that mock object. In a language without any side effects, testing becomes a lot easier because you know that a particular function can't do anything apart from on its parameters and what it returns. So you can be quite confident that you can just, once you've written a set of tests for that function, that you don't have to go back and rewrite them. I think one of the benefits of TDD in Java is that it not only does it create a set of tests that you can run again, but the main benefit is that it actually forces you to create very simple Java objects that can be testable, and that you don't end up creating these very, very large conflagrations of mutually calling objects in mutable state, because at each point you're really testing something very, very small and creating very small functions, and that's the main value for me of TDD. And there's another aspect of Clojure which helps you when you're testing. One of the things that you can't do often with mock objects is cope with the situation when you're testing a piece of code, and inside the code there's a line there that's going new this other object, which could be a database connection, or it could be a call to a web service. How do you mock out that when people are putting logic in a constructor? And when that happens in Clojure, if some function is calling another function, and you really prefer it wasn't calling open database, you can say, well, actually, for the purposes of this test, open database means this. It doesn't open the real database, it just opens my pretend database. And you can then run your test. And all you've done is, if you remember my explanation of Lisp and those pigeonholes, and they've all named, you just take a pigeonhole and you just say, right, you're no longer this function, you're that function. And that allows you to create very, very effective test suites. Another kind of interesting observation was that I had was that we had a DBA working on our team who was very keen on writing some functions to do bloom filters, and he went off and did this, and we actually wanted to integrate it into the main code base sometime later. And so I took his code, and it was all a bunch of functions, simple functions, and I put them into the main code base. And I didn't have to refactor them or change the type system, because the type system was just maps and sets and lists. And it just worked, and never had to change it. And I'd never had that experience of going to a Java library, ripping out a bunch of functions and just copying them and pasting them into another code base. It would just have to do some degree of writing adapters or refactoring. And I think this malleability of Clojure, the fact that there aren't these libraries that have their own type systems. There's only one type system, and that is the simple data types. That's something that is really means that you don't end up having to have big libraries that adapt other libraries. You don't have to have adapters of Spring drivers or Spring wrappers onto libraries. Things just kind of communicate through simple data structures. Modularity was my main way of tackling complexity before I found Clojure, and I found that by breaking Java systems into very small, discrete components and enforcing that modularity through the build, that was really the only way I had of reducing large systems to something that could be managed. And there were tools that I used to use to detect cycles between dependencies in Java systems, like Structure 101. And I found that really before I could get going at trying to get a big code base under test and refactored, was to look for these cycles and to try and use them to target where we should do the most work. In Clojure, there are no cycles by default, and there can't be. It's impossible for a module in Clojure, two modules to be mutually dependent. One of them has to come first. And even at a micro level, within a module, you can't refer to functions that you haven't previously defined. There is a forward declaration feature, but I've never used it. And so what it forces you to do is create a very clean architecture without any cycles, and it enforces that throughout your code. And because dependencies are so well managed, that does mean you can lift code and bring out its dependencies, and you don't start this problem of pulling out a library and then finding you've got lots and lots of other things all kind of wired into it. You often find that code is very, very portable in Clojure. And finally, had an experience where once the Clojure system is running, that because of the way that Lisp works, it is just this pigeonholes and functions. So you can log into it and change those pigeonholes, and you can test things and try things out. And this is very much the way that Lisp programmers used to write programs in the 70s and 80s, where it was very much in the world of AI that they couldn't, for those AI problems that Lisp programmers were trying to solve, it was very much that they didn't know how to specify the problem. They had to kind of get into the environment and experiment and explore and try things out. And and systems today, as computers got faster and more powerful, really the idea of writing kind of dead code and then putting it through a compiler and then running it and then debugging it and then going back and writing the dead code seems to be, to me, somewhat outdated. If you can run a system up and then start building it from within, you get a lot quicker feedback of anything you might try to do. And these really, really fast, short turnarounds and this kind of agility is something that I think is a real win for dynamic languages like Clojure, or any languages that don't really require a compilation step. Even though Clojure is all compiled, it's not an interpreted language, it compiles for speed. Everything is compiled just in time. So you can just ship your source code, and the source code will get loaded up by the JVM, and just in time will get compiled by the compiler. So the compiler is kind of part of the runtime, rather than something that we do as a preparatory step. So really, I mean, I kind of question, is Java really a Lisp? And by Java, I don't just mean the language, but I mean the whole Java runtime. Because there's this famous quote by Guy Steele about dragging the C++ programmers half the way to Lisp. And I think the work that Rich Hickey has done with Clojure really proves this statement was true, that in fact to take them the other half of the way to a real Lisp was actually possible from the work of just one man. And the JVM turns out to be a very, very, very capable Lisp machine. The Clojure code runs extremely efficiently, and certainly the performance of Clojure is up there with in the ballpark of Java. Certainly, there certainly aren't orders of magnitude differences in performance like there is in some languages. And I think lastly, the thing that really struck me through my experience of Clojure was how much computer science opens up to you, and how many choices of paradigm that you have open to you. It gives you avenues to explore things you'd never really consider exploring in Java. And one of the ones that I've enjoyed learning about is logic programming, or declarative programming. And to finish up my mystery section, I wanted to just demonstrate visually what this really means. How can you do logic programming in Clojure? Now, this is a Sudoku board. How would you go about writing a solver for Sudoku in Java or in any language? And there are plenty of attempts on the web that you can have a look at and see how this is done. In Clojure, with a library called CoreLogic, I can show you a program that can do this in the space of one slide. And that's the last thing I want to talk through. So now we have the Clojure board on the right. And on the left, we have the program. The first thing that we do is we say, let's have 81 9 times 9 logic variables. We'll define what rows are by partitioning them by 9 slots. And then we'll flip that, and we'll use very, very quick transpose function as you apply map vector rows. And then we'll define what it means to be a square. And as we go down the program, number 1 says, please run, I want to get one solution. 2 says, I want to return all the values, or all the logical values. Number 3 says, each of those values has to be 1 to 9. Number 4 says the values that have hints applied to them, well, that's the value of the hint. So if you've got a 9 written down in the grid, then it's a 9. Otherwise, everything in a row has to be distinct. Or every row has to have a distinct number of values. Every column has to have a distinct number of values. And every square has to have a distinct number of values. And you can run this, and it will produce you a solution to the to the Sudoku puzzle. And this ability for Clojure to very succinctly solve difficult problems, for me, is quite an amazing advert for using it in difficult problems that I want to solve. So thanks very much. That's the end of my talk. Do you have any questions? Yes. Yeah, I think I just say just one thing on that, and that is that when you move from a statically compiled language to a dynamically compiled language, your fear is that all sorts of things are going to go wrong. And our experience was that actually there are times when a static checker would have caught something a bit quicker, but the value of a static type checker, particularly in Java, where the type checking isn't particularly advanced, the value is often overestimated. And the kinds of things that go wrong in systems are more down to mutable state. I think mutable state is a much greater problem in systems than of type mismatches. And particularly if your types are only primitive data structures, if rather than creating your own types, as what Java encourages you to do, if you can get by at writing everything in Lisps and maps and sets, and you've got data structures, implementations that are far better. I've talked to all the software transactional memory aspects of these things that are far better than you could ever write in your customer class or your employer class. Then the trade-off of not having a type customer but just having a map is worth taking. So that, in my view, static type checking it does cause us to write lots of these private objects that all have to have the hash code and equals, and they're all kind of in themselves not as capable as the best implementations of a primitive data structure like a map.